Hey everyone, today we're going to be talking about section 5.5, and the first part of this section has to do with linearization. And this really kind of goes back to a concept we talked about earlier when we were talking about whether or not a function would be differentiable. So just to kind of review, we talked about functions being locally linear. Okay, and so we already know that taking the derivative of a function allows us to find the slope of a curve at a given point. So that's way old news by now. Okay, and so this whole process is based on the assumption that if you zoom in really close, even the curviest of functions will look like a line. So if you remember, we looked back at two curves. We looked at the absolute value, and then we looked at something that was really similar to that. When we zoomed in and in and in and in, no matter how many times we zoomed in, this corner never came out of that absolute value function. However, when we looked at the other function, when we zoomed in really close, eventually that corner started to straighten out and resemble a line. Okay, so using this idea, we say that, and I'm going to say we say that a differentiable function is locally linear. So again, the idea being that if we zoom in really close, that function will resemble a line at a given point. So that's basically the premise for this whole idea of linearization. And so I'm going to kind of give you the definition, and then we're going to talk about what it really is saying. Okay, so for linearization, if f is differentiable at x equals a, so some point a, then the graph can eventually be approximated by the equation of the tangent line at x equals a. So, for example, if I have some function, and I'm just going to use square root of x because we'll be kind of referring back to it later. Let's say that I have my tangent line here at x equals a. If I want to approximate the value of a function at a point close to a, so let's say I want to evaluate or approximate the value of the function at this point, I can use the tangent line because for points really close to a, that tangent line is going to give me a good approximation of that value. Obviously, I wouldn't use it for points far away from a because the further we get, the worse that approximation becomes. But this is going to work for points close to a. So all we're doing is using that tangent line to approximate the value of the function. So now, I need to write the equation of the tangent line, right? And we know we need two things. So here we've already been given the point, and then I need the slope. Well, we know the slope is just f prime of a. So the equation of that tangent line is going to be y minus f of a. That's equal to our slope, f prime of a, times x minus a. So again, that's old news. That's just the equation of our tangent line. And so to get our linearization, all we do is rearrange that equation. I'm going to move my f of a over to the right side by adding it. So I get f of a plus f prime of a times x minus a. And now instead of calling that y, I'm going to call that L of x. Right? We call that equation the linearization of f at point A. And again, I want to make sure we make a note here. We're using the linearization of a function to approximate the value of a function very close to the point of tangency. Again, this is only a good approximation for points that are close to the point of tangency. The further away we get, the worse that approximation becomes. So let's go ahead and see what some problems would look like. Now I'm going to change some things here. I want to just make this square root of x, and I want to center that at x equals 1. Okay, so what this question is asking, it wants us to find the linearization of f of x equals square root of x at x equals 1. And again, that point we call the center of linearization. Okay, so first we're going to find that linearization. And remember, that linearization is just an equation. It's basically the tangent line rearranged. So the linearization itself is an equation. Once we get that, we're going to use it to approximate the square root of 1.02 without our calculator. And then we'll pick up our calculators to see how close is that approximation. Right, and we think we should be pretty close because 1.02 is close to that center of linearization. So here we go. So if I'm going to find the linearization, remember, we start with the equation of the tangent. Okay, and so again, if we're writing the equation of a tangent line, we need two things. We need a point. Well, since they gave us our x value here, our center of linearization, really that's up here, what we called A. So our point is 1, and then if I plug that into f of x, f of 1, square root of 1 is just 1. So there's our point. Now we're going to find our slope. So we know f prime of x equals square root of x, right, which is just x to the 1/2. Sorry, this is f of x, a square root of x, so f prime of x is 1/2 times x to the negative 1/2, or 1 over 2 root x. Scoot this up and refocus a bit. Okay, so now my slope at x equals 1 is 1 over 2 times the square root of 1, or just 1/2. So now my equation of the tangent line is y minus 1 equals 1/2 times x minus 1. So to get our linearization, our equation, remember we're just rewriting this formula. So we call this L of x. My 1 gets moved over, so now I have 1 plus 1/2 times x minus 1. So that's our linearization. So now we're going to use that to approximate the square root of 1.02. So the square root of 1.02 is approximately L of 1.02, right? We said we're using this equation to approximate that value. And so that's equal to 1 plus 1/2 times our x is 1.02 minus 1. So if we simplify it, we have 1 plus 1/2 times 0.02, which is 1 plus 0.01. So our approximation is 1.01. We're saying that the square root of 1.02 is approximately 1.01. And so now we could go to our calculators to verify that. And if I do that, square root of 1.02, we can see is very, very close to our approximated value. So that's the whole idea behind linearizations. We're just using it, using that tangent line to approximate the value of a function. So I've got a couple of slightly different examples here. Okay, same idea. We're still using linearizations or linear approximations to estimate these values. But these look a little different. In our first example, we got the equation of the function, and we are also given the center. But we're not given that in these examples. So the first thing I need is a function. So if I look, obviously I'm dealing with a square root here. So my function, my f of x, is just going to be square root of x. Now, I need to find a center of this approximation. So I want to find some value that's close to 123 that's actually a perfect square. And so for this example, my center, I'm going to choose x is 121. That's a perfect square, and it's close to 123, so I should get a pretty reasonable estimate from this. So now I've got my function, I've got my center, so now we're going to come up, again, this is all based on equations of tangent lines. So again, we need two things. We need our point. So my x is 121. If I plug that into my function, square root of 121 is 11. So I have a point. Our derivative, we've got the same equation of before, we know is 1 over 2 root x. So then our slope at our center, 121, is just going to be 1 over 2 times the square root of 121, which is going to be 1 over 22. So now I have a point and a slope. Again, we're just going to write our equation of our tangent line. So y minus 11 equals 1 over 22 times x minus 121. So now our linearization is just 11 plus 1 over 22 times x minus 121. So that's the linearization. Now, we haven't answered the question. We haven't given the approximation yet. So that's what we're going to do next. So now, we said we wanted to approximate the square root of 123. We know that's approximately L of 123. And so that's going to be 11 plus 1/22 times 123 minus 121. So we're going to get 11 plus 2 over 22, so 11 plus 1/11. And so common denominator, I'm going to get 121 plus 1, 122 over 11. So that's our approximation. It's about 122 over 11, which if we look at a decimal, okay, we have 11.09 repeating. Okay, so now that's our approximation. Now, we can check that. If we take the actual square root of 123, again, we come out very, very close, so we know our approximation is correct. All right, last example. Very similar to this equation, we just have a slightly different function, and again, the idea is to come up with what our center is going to be. So now for my last one, my function now, we're dealing with the cube root of x. And so for my center, I need something that's a perfect cube and it's close to 123. So I'm going to pick x is 125. I know the cube root of 125 is going to be 5. So I have a perfect cube and I'm reasonably close to this value. So again, we'll go through our same idea. To get our equation, we need a point. So I have 125. Cube root of 125 is just 5. I need a slope. So for that, I need my derivative. So I have 1/3 times x to the negative 2/3. I'm just going to rewrite there. So now f prime of 125 is just 1 over 3 times 125 to the 2/3. So now to evaluate this, I know the cube root of 125 is 5. 5 squared is 25, and 25 3 is 75. So our slope is 1 over 75. So equation of tangent line is next. Y minus 5 equals 1 over 75 times x minus 125. And I'm simply going to rewrite that to get my linearization. So 5 plus 175 times x minus 125. That is our linearization. Remember, that's just the rewritten equation of the tangent line. So now we're going to actually do the approximation. I'm trying to approximate the cube root of 123, and I know that's approximately L of 123. So I'm going to substitute into my equation. 123 is going to go in for x. Let's see, so I get 5 minus 2 over 75. Let's see, 375 over 75. So 373 over 75 is our approximation. So we would say the cube root of 123 is approximately 373 over 75. Let's see, 123 to the 1/3. So our actual is 4.973, and our approximation, again, we come and see that comes out very close. So that's the idea behind linearization, just using that tangent line to approximate values of the function. And of course, we'll get practice working through this tomorrow.